Hello and welcome to the channel Understanding Concepts of Physics. We have been doing oscillations since past few videos and we have been completing velocity, acceleration and displacement concepts in the previous videos. If you have seen these videos, then we have also completed the minimum and maximum acceleration as well as for velocity and as well as for displacement. Go and watch the videos in case you have not done so, and if you have any doubts and difficulties, you just keep on commenting and I will be happy to help you in those problems. Today what we are going to do is a small derivation, linear simple harmonic motion as a projection of uniform circular motion. So it's a small derivation, so I have written it entirely, and you initially I would say it's a small derivation, but if you see that the derivation looks slightly bigger on the end, the reason is I have considered people who are not mathematically inclined. So in case if you are mathematically inclined, if you know what derivatives, trigonometry works like, then you can skip the few number of steps and you can just go back to the direct answers. Now let's just quickly see what I have drawn over here. So what I have done is I have just taken a circle. So this is my circle. I'll just redraw this diagram. This is this circle, and in that I have taken two axes. So this is two axes, so x-axis and y-axis, and I have taken a particle, let's say at point P, and the point P's projection is somewhere, this point P's projection would come somewhere around here. This is P, this is M, and this is my radius. I'll call this as O, this A, this is B, and after a certain time the particle P is going to move on this circumference of the circle and reach at point P dash. After moving the particle, when it is moving like this, moving, and then it has reached at this point, the projection would come somewhere around here. So I'll call this as M dash, and this is my radius, and I'll call this angle as alpha, this as theta, and this as beta. So this is what the diagram has to say. So I'll just read on in order to make you understand how the diagram has to be made. So first draw a circle, draw an axis, take a point P, move it from some other point. So this is what it is. So let's see now. Going back to the diagram, you can just freeze the screen, or you can just take a photocopy of this in case if you wish to draw it personally. Then consider a particle. Now in here what I have done is whatever is happening, I have just mentioned that in the words. Consider a particle moving in uniform circular motion. Then P and P dash are the initial and the final positions. M and M dash are the projections, so on x-axis, and OA, OB, OP, OP dash is A, which is the radius. So I am just mentioning that. So O say OA, OP, OP dash and OB, all these are radius, which I am writing as A. Now there is a hidden purpose in writing radius as A and not as R, and we will come to that part very shortly. Alpha is the initial angle made by the radius with the x-axis. Theta is the angle covered in some time. So the particle, since the particle is in a circular motion, it is moving like this back on the circle. So in, let's say in some time, it is coming from O or P, like it is coming from P to P dash. So that time requires is T. Omega is the angular velocity and theta is the angular displacement. So we know the formula that omega is equal to theta by T. So theta would be equal to omega into T. So theta would be equal to omega into T. So omega is the constant angular velocity, because I am assuming that the uniform circular motion, in uniform circular motion the angular velocity is constant. Now in the next step to follow, what we are supposed to do is, in triangle P dash M dash O. So if you see this triangle P dash M dash O in this red triangle, I'll find out what cos beta is. So cos beta is adjacent upon hypotenuse. So it is OM dash upon P dash O. So OM dash upon OP dash, that is x upon A. Why is it x upon A? Because the distance is x on the x-axis and this is your radius, which I am writing as A. Then this is x upon A. So x upon A and on this side it is cos beta. Now what I can do is for cos beta I can say that the angle for this axis is 180. This is 180 degrees and I want beta. So what I'll do is 180 minus this angle. Like if I wish to find out this particular angle, what I'll do is I'll take 180 minus this angle. So let's say if this angle is 120 and I know that this whole angle is 180, so that is 180 minus 120, I'll give it as 60 degrees. So what I've done is cos of beta can be written as pi, that is 180, minus that 120 which I have just set for the example, that is theta plus alpha. Why is it theta plus alpha? Because if this is 180 and this is theta and alpha, so I can say my beta is theta 180, that is pi minus theta plus alpha. So wherever there is a beta, I have just replaced by theta plus alpha, that is x by a. Now cos pi minus theta plus alpha is nothing but cos theta plus alpha into minus of that. Now this comes under trigonometry formulas, that cos of pi minus x is equal to minus cos x. So in case if you are not familiar with this, try to read some books on trigonometry and changing the angles. Then comes theta is replaced as omega t, so I have replaced that. I want x, so I'll take this a on the other side, so it will be minus a omega cos omega t minus a cos omega t plus alpha, and x is as it is. When I reach at this point, you should remember that when I differentiate the position, that is x, I get velocity, and when I differentiate the velocity I get acceleration. So, and if I get acceleration, I can just multiply that acceleration by mass to get force. So displacement, if you differentiate, you get velocity. Velocity, if you differentiate, you get acceleration. Acceleration you multiply by mass. When you multiply by mass, you get force. And acceleration, if you integrate, you get velocity, and velocity, if you integrate, you get displacement. So I'm going to differentiate this. So if differentiation is not your problem, then you can just write this step directly. Yes, if differentiation is your problem, then minus a omega minus a, I just made a mistake. No. See. So what has happened here is a is kept separately, and you will wonder where is this minus sign. So derivative of cos is minus sign, so that minus and minus will get cut and you'll get plus. So derivative of cos x is minus sin x. So this minus and this minus gets cut, so that will become plus. Sin omega t plus alpha is as it is, and there is a chain rule here, so derivative of omega t plus alpha will remain as it is. Now a as it is, sin omega t plus alpha as it is. Now you will wonder why this omega has come over here. So if you see that there is a u plus v rule, derivative will go to this as well as this term as well. But since alpha is a constant, derivative of a constant is 0, so this goes off. And derivative of let's say omega t, it would be derivative of omega t would be omega, like how derivative of 4x is 4, derivative of 10x is 10. So derivative of omega t is omega, so that omega I have written it over here, and derivative of a constant is 0. Now similar manner I have differentiated this with respect to t to get the acceleration. So you can just follow it up like this. A omega as it is, so a omega as it is, I have kept it over here. Sine is differentiated, so sine will become to cos omega t plus alpha, and there is a chain rule in omega t plus alpha, so derivative of omega t is omega. This omega and this omega will give me omega square, that's why you will see that omega square has come up. And derivative of a constant is 0, that's why we have not written. So I have done this part directly, however this I have showed you how it is to be done. Now here there is a manipulation. I am just manipulating some aspect because I see there is some plausibility in my equation. First of all, cos omega t plus alpha is as it is, a is as it is, and omega square is as it is. What is new is minus and minus. So minus into minus is plus, which I am having in the previous equation. Now why did I adjust this minus over here is because I am seeing that in my displacement there is a minus sign over here. So if I call this equation as equation number 1, I'll call this as equation number 1. So this equation is equation number 1. So if this is equation number 1, then I can say that okay, this is coming from 1. So this is going to come from 1, from equation 1. So if you have followed up till now, acceleration comes out to be like whatever this term is, this is your displacement. So I have replaced that as x. Now minus omega square x is something I got acceleration. Mass into acceleration, even I am multiplying both sides by m. So I have multiplied by m, multiplied by m. Mass into acceleration is force, and instead of writing with two constants, that is m and omega square, I am just writing as k. So minus of kx, and if I remove this constant, the equal to will become proportionality sign. So force is depending on displacement, and it is always in the opposite direction to the displacement. This is only happening in SHM. So whichever body is following this equation, definitely that body has to be in SHM. So any particle following above equation is in linear simple harmonic motion. So if you see, I had never mentioned that particle was in simple harmonic motion, but I always said that the body is in a circular motion, uniform circular motion. So when you see a body in a circular motion, actually it's just a projection of uniform circular motion. It is an SHM, but if you see along the diameter. So if I see a particle which is moving in the circular motion, this is because I am watching it from the top. But suppose, let's say, okay, if I am watching it from here, this is the eye, then, and this particle is moving along the circumference of a circle, then for the time being I will see that the particle at this point is here, and the particle is just going up and down like this. The particle is just going up and down. And suppose if I see the particle from here, let's say I am seeing it from here, this is my eye. So at this point the particle is here at point P, and it is moving along the circumference of a circle, but at this point the particle appears to be at this point. So when you are seeing from along the diameter, you will see that the particle, when it goes ahead, this particle moves here, and when it reaches here, it appears to be here. When it reaches here, it appears to be here. When it reaches here, it appears to be here. When it reaches here, it appears to be here. And when it reaches here, it appears to be here. And the particle is moving along the circumference of a circle, but it appears that the particle is moving along the diameter like this. And that is true even if you watch it from some other point as well. Like if you are watching it from here, the particle will appear that the particle is moving along the diameter, oscillating along the diameter, moving circular motion. So uniform circular motion are very related to SHM, but along any diameter. This is one thing. So just remember that this equation is only valid for simple harmonic motion. So any body which follows this equation has to go into simple harmonic motion. That's it for today. Thank you so much for watching the video. And yes, one more thing I just missed out is that you can also do that by some other means as well. Like you can make the particle come here and then you can draw the projection. You can make the particle come here and draw the projection. You can do it by many methods. You might be following some different boards, and in that books you might be finding the diagrams are slightly different, but the overall major concept remains the same. Thank you so much for watching. Subscribe the channel in case you have not done so, and if you have been through so much long video. Thanks so much for watching. You can remove few steps if you want to, and make your own notes. Thank you so much. Have a nice day. Bye.